slide did not get recorded yesterday. Okay. Yeah, so in terms of composition, cement is composed of a few major oxides like calcium oxide, silicon dioxide, aluminum oxide and iron oxide. As you can see, the primary composition of cement is in terms of lime or calcium oxide. We have nearly 2/3 of cement is composed of calcium oxide. Apart from these 4 major oxides, you can also have significant quantities of magnesium oxide, depending upon the source of your limestone, of course. And there are alkalis present to the tune of about 0.3 to 1%. More typically, what we see in Indian cements is that the alkali contents are around 0.6 to 0.8% in India. But several cements could have higher than 1% also. Okay. There are some problems with very high alkali cements, which of course we will discuss in the course of this series of lectures. Cements abroad typically tend to have a higher alkali content. Now, alkali content in cement helps to actually enhance the early age strength development of the cement, and that is why one has to be very careful about balancing this well. Now, where are these alkalis coming from? Mostly what happens is these alkalis are present in the raw material in the form of alkali sulfates. Alkali sulfates are usually present as impurities in the raw materials, and these basically come into the mixture, compound mixture that we actually have, right. So, the sulfates that are indicated here are not just from the gypsum that we add in the final stages, but also could be from the alkali sulfate sources that are available as impurities in the concrete, in the raw materials. Now, in the kiln, as we discussed earlier, there is going to be a combination of these oxides to form the primary phases: tricalcium silicate, dicalcium silicate, tricalcium aluminate and tetracalcium aluminoferrite. And if you look at the overall composition, if you add up your C3S and C2S together, typically around 80% would be C3S plus C2S, irrespective of the type of cement. We will talk about different types of cement, but in all cements, if you combine C3S and C2S together, it will be more or less close to 80%. Again, C3A plus C4AF together will be about 12 to 15%. Okay, 80 to 85, let us say 12 to 15%, and gypsum is around 3 to 4%. That is the amount of gypsum that is available in the mix that we have. Okay. And of course, as I said, in OPC, up to 5% of additives or performance improvers are permitted. Okay. Performance improvers typically are limestone or sometimes fly ash. Okay. So, these are lowering the overall CO2 impact of the cement. But later we learn that at this 5% level, they are also able to provide additional benefits. Okay. Right. So, as far as cement is concerned, C3S is the major component in cement. More than 50% is C3S, and C3S is also responsible for early strength development, right. Now, of course, in projects, people used to be happy to wait for years earlier, right. When we built our old monuments, those were built over years, right. The monuments did not come up in like 3 months or 2 months or 1 year or 2 years or whatever. People used to wait years for monuments to get constructed. As time passed on, we wanted to speedily construct and finish things fast. So, nowadays you have monuments and structures that are produced or constructed in very little time. And because of this, the importance of C3S as a component of cement is only increasing, because C3S is the one which leads to early strength development. Okay. And this early strength development comes from the fact that C3S has a high reactivity because of its irregular structure. We saw a picture of cement clinker earlier, in which C3S had an irregular structure, polygonal structure, which leads to a high reactivity. Okay. And high reactivity also means it has got a high heat of hydration. What do we mean by heat of hydration? It is the heat liberated when cement reacts with water. So, cement is composed of different compounds. So, the heat that is liberated when cement reacts depends on heat liberation of individual compounds. The compounds that react faster liberate a lot more heat. Okay. You might have seen this with lime, right? Slaking of lime. We typically add water to calcium oxide. there's a massive heat evolution that happens from that process. Same thing even here in cement also, there's an exothermic process which releases heat. Of course, in terms of crystal structures, this is not the right platform for the discussion, but yes, several crystal structures are possible with C3S. And as we were talking earlier, alite is nothing but impure C3S, which has other impurities. Some of the impurities are provided here just for your understanding. We are not really going to discuss this in more detail. C2S is a less irregular structure that's more rounded, as we saw from the pictures of the cement clinker that I showed earlier. And because of this more regular structure, it's got less reactivity. Okay. Overall substitutions of oxides can be up to 4 to 6%. So, in B-lite, C2S can have impurities in the form of these oxides. And again, because of the formation and the presence of different types of impurities, the polymorphs exist. There are different forms of, different crystalline forms of C2S or B-lite that may exist. C3 and C4AF, as you saw in the pictures earlier with the clinker, they are not that easy to distinguish as compared to your C2S and C3S, which are much larger crystalline particles. C3A and C4AF are also crystalline, but they are small enough that they are present almost in an intermixed kind of a fashion. Again, in terms of crystalline composition, pure C3A will have a cubic structure, but with impurities it can also get other crystal forms such as orthorhombic. The issue is heat of hydration. Okay. Amongst all cement compounds, C3A has the highest heat of hydration. So, if you were to produce a low heat cement, what would you do? Reduce the C3A and preferably also reduce C3S, because C3S also liberates a lot of heat, it reacts fast. So, if you have to produce a low heat cement, right, what applications would you need low heat cement for? For mass concrete, dams, right? In such cases, you need a low heat cement. And such cements are produced typically with lower C3A and C3S contents. Okay, C4AF is not really a component that matters too much in the long run, except that of course, to keep this balance of C3A and C4AF, like I said, when you want low heat, you reduce C3A, but when you reduce C3A, the C4AF content will get pushed up slightly. So, it does that balancing of the aluminate fractions in the cement, but otherwise it does not really have a major significance with respect to the hydration reactions. Okay, you will find even if you take a cement which is or concrete structure which is like 50, 60 years old, if you take a small microscopic image from inside, you will find that much of the C4AF is present as it is in the original cement. It is not reacted at all. That is because iron is present and this iron makes it highly insoluble. Okay. So, cement particles have to first start solubilizing and then they react. So, C4AF is a phase that does not solubilize easily. As a result, you will not find the iron particles having or C4AF phases having reacted much even in concrete that is very old. Okay. So, there are several ways of classifying cements. I am just giving you some principal classifications based on ASTM, Indian standards and European standards. ASTM classifies regular cement, which is as per the ASTM specification C150, into 5 types. One is general purpose, which in India we call as ordinary Portland cement, right? And then type 2 is moderately sulfate resistant and moderate heat of hydration. Essentially, this means lower C3A and C3S. Okay. Then you have type 3, which is high early strength. How will you increase the strength of cement? You increase more C3S, right? Any other way in which you can increase strength gain rate of cement? You can grind the cement finer, right? Increase C3S, finer cement. So, more C3S and finer. And then you have type 4, which is low heat of hydration or low heat cement, right? So, obviously here lower C3A and C3S. And type 5 is sulfate resistant. If you, when we discuss about mechanisms, you will see that sulfate resistance especially is brought about by the fact that you use a cement with lowest C3A content. The aluminate content is reduced to the lowest level in the case of sulfate resistant cement. Okay. So, these are simply call it type 1A and type 2A. Okay. Just to give you this same thing in a snapshot of the compound composition. You can clearly see here that compared to type 1, type 2 has lower C3S and C3A. Type 4 also has lower C3S and C3A, but the C3S lowering in type 4 is much more than in type 2. So, obviously, when you lower C3S, you increase C2S. The silicates typically will add up to nearly 80 to 85%. Okay. So, if you are lowering C3S, you are increasing the C2S. And then type 5, as I said, lower C3A and sometimes also lower C3S as compared to type 1 cement. So, this is the overall chemical composition, which is quite similar if you look at other standards also, like BIS also has a sulfate resistant cement, BIS also has low heat cement, high early strength cement. Most of the characteristics are quite similar across different standards, right.